So let's go to this place, the place of movers. So movers are algorithms that move things around. The simplest way to move things around is probably to copy them. So std copy is probably the simplest algorithm in the whole library. Takes takes one collection with a beginning and an end, and the output iterator of a second collection, or back inserter, or stream iterator, or whatever, and copies every element of the first collection into this output iterator. There's also std move. Like, we know std move, like std move, but there's also std move, the algorithm. And it takes a beginning and end and an output iterator, just like std copy, and it calls the usual std move on every element of the input collection. So after std move, the algorithm, all the elements of the input collection are moved. And to swap the contents of two ranges, there's swap ranges, and they all obviously have to be the same size. Now, a little exercise. Let's say that we've got a collection at the top, 1, 2, 3, all the way up to 10. And we would like to write some code and use an algorithm that we've seen from the beginning of that talk up until now to turn it into the collection at the bottom. So we want to copy the first 5 elements 4 positions down. Which algorithm do you think we could use to do that? Come on, there's less than 105 possible answers. Yeah. Copy, absolutely. So we'll use copy. I thought to use copy as well. And then I think it crashed when I used it. So let's see what happens, what's happening. So the first thing copy does is to copy the first element, right, to the output. So I don't know if you were thinking about that, but I put as an output iterator begin plus 3. And then we've lost a value. We've lost 4, right, which is annoying. What we would like to do is to copy, but starting from the last one, right? Because we didn't care about the 8 that used to be there. And then move all the way back up, yeah? So what we would really like to do is to copy, but backwards. That's what we're going to say, right? Yeah, copy backwards. That's pretty much the same thing. And there's also move backwards that does the same thing, but moves. Right, so that's the movers. Now, just down around the corner, there's the value modifiers, which I would have expected to be more numerous, but there's just 4 of them in a quite large piece of land. So those guys actually change the values inside of a collection. So how can we change the values inside of a collection? One easy way to do that is to put the same value everywhere. That's what fill does. It takes begin and end value and copies that values all the way through. Another way that's a bit similar in spirit is to use a function that can be called with no argument, and we call that function once for every element of the collection. That's generate. Another way to fill a collection that's quite useful to have, like, I don't know, unit tests, stuff like that, to have quickly a sequence of values is iota, which has a funny name, I think. It takes begin and end value, put that value at the beginning, and then increments it until it fills the whole collection with increments. And finally, there's replace, that quite expectedly replaces the values in a collection. Like replace 42, 43 will replace every 42 by a 43 in a collection of ints. Right, now jumping above the water, there's this island of the structured changes. What I call the structured changes is is the algorithms that after they've done that job, the collection doesn't look the same, even from afar. So there are two of them, remove and unique. Remove is used to remove values, but it has something peculiar with it. Since STL algorithms only access the iterators of a collection and not the collections themselves, they can't change the size, for example, of a collection. They can't perform an erase in a collection. All they can do is to change the values between the begin and the end. So what remove does is to pull up the collection by leaving only those that should not be removed. So if we want to remove the 99s, we use remove, begin, and 99, and it will pull up everything that's left without the 99. And what's at the end is not specified. We can't rely on it. It could be the element that were there before, it could be 99s, it could be anything else. It could change, it could vary from compiler to compiler, from version to version, so we can't rely on that. And to actually remove those elements from, say, a vector, we have to call a method on the container, like erase on a vector. We'd like to erase all the elements that are crossed out. And to do that, remove returns an iterator that points to the first element that's here crossed out. So we have to erase between what remove returns and the end, which is quite of a mouthful of code to remove the 99 in the collection, isn't it? I think that we should not use that code, and we should wrap it into a function with a nicer name and use this in our everyday code. I reckon there's been a proposal by STL, Mr. STL, the guy, to add those functions to the standard. It hasn't been accepted yet, so until it is, if it is, we should just wrap this function. It's quite another thing to do. If you want to grab the code, it's been published on Free on C++ last week, I reckon. Unique does something quite similar. It removes the duplicates in a collection, or more precisely, the adjacent duplicates in a collection. Right? So if we do unique here, this collection has several 99s, and it will remove only the adjacent 99, because it has a linear complexity. It will only traverse the collection once. And unique will also pull up the values that are to be left and return an iterator to the values the values that are crossed out. Those values, we can't rely on them, just like remove, and we have to erase them. Quite a bit of code, not much, and we should package that into a function with a better name. Whether unique is a better name, I'm not sure, but we should at least package that into a function. I've got a question there. Sorry, I couldn't hear that. Indeed, 1 was not removed. That's good observation, and it's not removed because there's no adjacent 1s in the collection. Thanks for that. We've unlocked a new rune, copy. We've seen all the algorithms that are combined with copy in the STL Algorithms library. So copy, you can tack it on an algorithm like those algorithms, and it creates new algorithms that do the same thing, but in a new collection. So like remove or unique or replace or whatever, they operate in place. Those guys, they leave the collection untouched, and they take an output iterator and they produce the output to that output iterator. We've also unlocked if that as a predicate, so where, say, find, for example, was taking a value, find if takes a predicate, but does essentially the same thing. And we're going to go to that part we started with the talk with, the Lonely Islands, with for each and transform. Let's start with transform. There's nothing wrong with for each transform. The reason why I put them on Lonely Islands is because I couldn't see in what family they would belong. I think they sort of like separate, even though it's not a problem in itself. So transform essentially applies a function to the elements of a collection. So it takes a collection, big N, a function, f, and an output, like an output iterator, such as this back inserter here. And it produces the application of that function to every element in the collection. What's a bit less famous about transform is its other overload. The one that takes two collections and a function that takes two parameters, right? So it applies that function just like transform with one input collection to the two collection by feeding the two collection into F for each element and producing the output. Yeah, like for example, if you'd like to sum the elements of two collection 2 by 2, you can do that with one line of code with transform, and F would be stud plus. And that's for each. And for each, if we think about what it does, so for each takes a begin, an end, and some piece of code, a function, it could be a lambda, for example, or a regular function. And it applies that function to every element. What's interesting to note is that it doesn't care about what F returns. So for the purpose of for each, F might as well return void. Now, what does a function that returns void do? Anyone an idea? Yeah, exactly. Side effects. For each is made to perform side effects. Now, are side effects a good thing or a bad thing is absolutely not the purpose of that talk, even though I think that some cases are useful with side effects. But for each is made for doing side effects. That could be side effects on the elements themselves, modifying the elements of the collection, or that could be side effect in the more general sense of sending stuff to logger or whatever, right? But for each is made for side effects. Using for each for making anything else, such as a partition or a find or whatever, is not the right usage of for each. There are algorithms that are more appropriate than for each. And if there's no algorithm more appropriate than for each in the STL algorithms, then there are algorithms outside of the STL library, and we briefly talk about them in a minute. Okay, so we've been literally all around the world. We've started down there, we've been in the land of queries, the glorious quantity of algorithms and sets, movers, the value modifiers, and the structure changes, and even up there. There's only one place we haven't been yet,